Okay, I intend to finish the problem that I was doing this morning with this video. So anyway, what I do is I need to find the direction for this spring force. If y and z are both, so we had y, if you remember, down this way. Let me see if I can draw the picture since it's not up on the blackboard. Okay, there was a cantilever beam, and it had a spring. This was a distance L. This was a distance L to the end. This was K. We called it K1. There was a damper, which we called C1, right there, and this was a rotation. This angle here was theta. It came up on a rod to a rotational disc. So this thing rotated. This was actually connected right there. And on the other side, it came down through a rod, and then there was a spring attached right here and a mass at the end of that. We were at the point where we said that this was an angle which we called beta. Okay, sorry for the interruption. I was a little bit interrupted there. Let me see if I can pick up from where we were. Okay, so I have this angle beta, which is defines the rotation of that disk, and then here I also defined a variable y, which would be the displacement of this point right there. And on the other end, I have a I think I defined a variable z up from the mass. Okay, and the objective, or the idea was that I mentioned in class is, you know, use as many variables as you need to in order to make the calculations and whatnot work out for you. So anyway, here I was doing the spring force. You know that the y is required in the equation because if you hold z fixed over here, so if you hold the z fixed and you move the y, it changes the spring. And also if you hold the y fixed and move z, it changes the spring. And so you know that y and z are both in the formula for the spring force. To determine whether they're plus or minus, then what I would do is I would move the y and z in both of them in a positive one direction, and I'd ask what happens to the spring. If you look at the diagram over here, if you move the y and z both in the positive 1, you squash the spring by 2. And so whatever formula I put in for y and z, I should get the number 2 when I have a 1 for each of them. And so that's why I'm adding. Okay, so now that I know that they're added, what I do is I pretend like y and z, y plus z is positive. So let y be 0, let z be positive 1. If that's the case, you look at the diagram again over here, and you can see that if y is 0 and z is plus 1, I have compressed the spring. To compress the spring, I've pushed the spring. If I push the spring pushes me. And so the spring arrowhead goes in this direction. So that's the free body diagram of that disk. And then I also promised I would do a free body diagram of only the disk and not the rod. So let me do that. I'll put it in red just to show that you're going to use one or the other, but not both. So if you did it like this, you'd still have these forces in the middle because of this guy. You'd have the equal and opposite tension down, which is equal and opposite to this guy. And then over here you have a rod, which is not in the free body diagram, and so it's going to create a tension or a compression. I don't know. I don't know what direction it is. I don't know anything about it, so I'm just going to draw it up, and I'm going to call it T2. So this is the tension from rod 2. Now I also have a rod, okay, and so I'm going to draw a free body diagram of the rod. So here we go. There's the rod. I have an equal and opposite force up here, which is T2. And then down here I have the spring force, and so I'm going to now have the spring force just like I had before. I'm going to end up with exactly the same values for the equation, and arrowhead like this. So I have either the two red ones or the blue one, whichever one you want. And so now let's do the free body diagram of the last guy, which is the mass. So we'll say, okay, here's this mass. I don't put in gravity because gravity is not causing the oscillation. I'm measuring z from static equilibrium, and so I'm ignoring all free lengths and all that stuff just like usual. So here what I've got is the only force is the spring force. It's got to be equal and opposite to either the red or the blue. So those are up, so this guy is going to be down, and the formula is K2 y plus z. Okay, so now that I have the free body diagrams, I'm going to write summation of forces or moments or whatever is appropriate for it. So the first thing I'm going to do is we'll do this this system up here, and because it's rotating, I'm going to sum moments. I would like to sum moments around the end. I can, because that point is fixed, so I'm going to sum moments around the end. The end right there. Alright, so here we go. I'll put them in black. So summation of moments is going to give me a spring force K1 L theta. That's the force. The moment arm is distance of L cosine theta, and cosine is equal to 1. So that's the moment arm, and that is tending to turn in the counterclockwise direction. Clockwise is positive because of the way the arrow, the angle is drawn. So this is the clockwise is positive. So this would be a negative moment. Then I also have the damper, which is going to be C1 L theta dot. Its moment arm is also L cosine theta, which is just L, and it is also a negative moment. Let's see, I also have a tension. So I have the force of T, and its moment arm is 2L, and it is also a negative moment, and that equals the moment of inertia around the end, the left end, because that's where I'm summing moments, so that's where I take the moment of inertia. Let's call that J, not quite sure what we should call it. I'm going to call it J1 because spring 1, damper 1, they're all connected to body 1. So it'll be J1 about the left end. I'll put left, L-E-F-T. And I'm just going to call it J1 from now on, but it's around the left end times the angle, the angular acceleration. It's 2 dimensions. It's real easy. It's theta double dot. Okay, so that's that equation. Now let's write the equation for the blue free body diagram. So we'll take the blue pen, and for the blue free body, what I'm going to do is say, okay, we're going to sum moments. I'd like to sum moments right here around the center, and that's okay because the center is fixed. So I'm going to do that. So that I'm going to have T. The moment arm of this guy is going to be, the radius is big R. It'll be R cosine of theta, but cosine of theta is equal to 1 for small angles. And that is, since beta is in the clockwise direction positive, this is going to be a negative moment. I have the spring force over there, which is K2 y plus z times its moment arm, which is going to be R cosine of theta, so it's basically R. And that is also a negative moment. And that's all, so that equals the moment of inertia. I'll call it J body 2, we'll call it J2, and it'll be about the center because that's where I'm summing moments, on the center, and this will be the angle beta double dot, beta double dot. Okay. Next, if you wanted to, you're either going to use the blues or the reds, but let's go ahead and do the reds. So if I were to draw the reds, this is what I would have. I would have a minus T R, a minus T2 R. That's it. So that equals J2 around the center, beta double dot. And then for the other red one, that is not rotating, it's just translating. So I'm going to sum forces, and I'm going to use the variable y, the blue y. And so I'm going to say, all right, y is positive downward, and so this would be a positive T2 minus, because it's pointed up, minus K2 y plus z, and that's it. So that equals the mass of this guy, which is probably 0, but mass of the rod times y double dot. If it is massless or very lightweight, then the term on the right hand side would be 0. No big deal, but it's the same thing. Okay, so I'm either going to use the blues or I'm going to use the reds. Incidentally, if the rod does have mass, then this J would be the J for the disk plus the moment of inertia of the massive rod that's over there as well. It's easy to calculate those. There are textbook formulas for it, or what you would do is you'd use the NX or some graphics program that would calculate it for you. Okay, so anyway, that's how you get that. And then I have one more term, the black mass, and so I'm going to write the equations for that guy. And since Z is up positive, I'm going to take up as being positive, so the forces are negative K2 y plus z. That's the summation of forces, and that equals the mass that's in that free body diagram, and only the mass that's in that free body, m3 times z double dot. Okay, so now what we'll do is let's circle or underline or identify the forces or the unknowns. So let me highlight them. So this guy here, theta, double dot, theta, I only have to count one of them, is unknown. I also don't know the t, which is a variable. The l's and j's and all that, those are parameters. I will look them up. The damper, I built the damper, I would know what the coordinate is, so that equation has two unknowns. For the next equation, I have beta double dot. I haven't counted y, and I haven't counted z, so I have those two as well. The t's been counted, so I don't have to worry about that. And then the last equation, so I'm going to use the two blacks and the blue. So the z, whoops, I'm sorry, let me see if I can undo that. Okay, so the z's already been counted, the y's already been counted, so everything else has been counted. So I have 1, 2, 3, 4, 5 unknowns. Right, so in that system I have 5 unknowns, and I have 1, 2, 3 equations. 5 unknowns, I have 3 equations. So I'm missing 2 equations. Okay, now this is a 2 degree of freedom system, I know that. So of my unknowns, I have theta, beta, and z, and y. So I have theta, flow motions, theta, beta, z, and y. I have 4 of the unknowns that are motions. I should only have 2. That tells me that there are 2 constraint equations that relate some of these motions. Okay, so now I have to go back in and look for constraint equations. So let's look back up here at our diagram. It seems reasonable to me that the distance that this thing, let's put it in red, the distance that this point moves right here is equal to the distance that this thing moves right here, or at least opposite directions. So for example, if the end point, this red end point, if it goes down 2 feet, then this blue point right here would go down 2 feet as well. Okay, so I'm going to write that equation. I'm going to put it in red. Okay, so the distance that the end moves, I'm going to put it in terms of the variables that I'm already using, theta, beta, etc. So the distance that red end moves is equal to 2L times the sine of the angle theta. Okay, so that would be 2L, 2L sine of theta is theta. If theta is positive, then the distance moves down. Okay, on the blue guy, I'm going to say that this thing has to equal equation for the blue guy. Well, okay, the distance that blue one moves in terms of beta is equal to the radius r times the sine of beta, which is the radius r times beta. Now this is almost right. And what's wrong is if theta and beta are both positive numbers, then this is, you know, the blue guy went up, but the end of the beam went down, and that's not right. So what I need is I need to do something like this, so that, for example, if theta is positive, beta has to be negative, right? So if theta is positive, beta has to be negative, and that's why I need to put a negative in here, so that if you have a positive number here, the formula will tell you that beta then is a negative number. Right, so now I've got that one. So that's one constraint. I'm looking for another constraint. Well, let's relate the y's and the z's. Okay, and that was not too hard. So what you do is you say, well, if y is a positive 1, z is a negative 1. That's pretty easy, right? So then I'm going to write that. So if y is a positive 1, z has to be a negative 1. So there's my second constraint. And so now I have 5 equations, the black, the blue, the second black one, and then the 2 bottom red ones. So that's 5 equations, and I've got 5 variables. So now I'm ready to go to Mathematica. Okay, if you were using the red equations, then you would have circling or identifying unknowns. Let's go in here, all right? So t has been counted, t2 hasn't been counted, so that's another unknown that I have. The y and z have already counted. The y double dot counted the y, counted beta, so that's it. So now if you were to use the 2 red equations instead of the blue, what you would have is you would have another unknown, which would be t2. Okay, so instead of 5 unknowns, you would have using the black, you would have theta, beta, z, y, and t, right? If you use the red ones, you have all of those unknowns, plus you also have the t2. So you're going to end up with 6 unknowns if you use the reds. But the number of equations, if you use the reds, you have the top black, you have the 2 reds in the middle, that's 3. You have the second black one, that's 4. And then you have the 2 constraints, okay? So you'd end up with 6 equations if you're using the reds. Okay. Before you write the bottom red ones, you would say that you have t2, t, theta, beta, z, and y. So you would say I have 6 unknowns. 4 of them are motions. You only need 2 of the motions because it's only 2 degrees of freedom. So you know that 4 unknown motions can be replaced with 2 constraints, and that's so you end up with the same conclusion. So anyway, you can either use the reds or you can use the blue. Makes no difference as far as Mathematica is concerned. What's one more equation? So anyway, let's now go to Mathematica and see what's happening. So let's see. I'm going to open up a new Mathematica window. Let's see, edit, new notebook. Okay. So all I'm going to do is try to solve these equations. And let's make it a little bit bigger so it's easier to see. All right. So first thing I'm going to do is quit. And now I'm going to try and type in these equations. I'll use the black ones. And I'm going to type them in as S equations. So So equations are, the first one is minus K1 L, TH is going to be my theta, L, minus C1 L S theta, L, minus T times 2 times L equals J1 S squared times theta. That's the first equation. Second equation, I'm going to use the blues, minus T R minus K2 Y plus Z R equals J2 S squared beta. Third equation is the black one, minus K2 Y plus Z equals mass 3 S squared Z. The last two are the constraints, 2L theta equals minus R beta. The last one is Y equals minus Z, close parentheses, hit Shift and Enter. Now I'm going to solve, and I think you can, you're anticipating, I'll bet you, what's going to happen. I'm going to solve the equations for the following things. T, let's see, theta, beta, there's 6 of them, right? 1, 2, 3, 4, no, 5, okay. T, theta, beta, Y, and Z. So those are my 5 variables. Now, what do you think is going to happen? 0. Why is it 0? Same reason I gave in class. When you're converting the differential equations into S equations, you're taking the Laplace transform, you're ignoring all initial conditions. So if you don't have something that gets it excited, nothing's going to happen. Okay, and that's what's happening here. Okay, so what do you do about that? Well, what you do about that is don't be foolish. Put in a forcing term. Okay, what's the easiest thing you can think of? Oh, maybe you would put in a force over here. You could do that. Just put in an F. Okay, you don't like that? Okay, then put in a torque here. Don't like that? Put it in somewhere. Whatever. I think the easiest thing probably is to put in this force. So I'm going to go ahead and do that. So what I'm going to do, you can put it anywhere you want, but what I'm going to do, just so I avoid that 0, 0, 0 business, remember, I'm going to put in a force here. Y down? No, who cares? I'm going to put it in there. Okay, so what changes? Well, you know, basically I'm putting a force here. Right? I'm applying a force here. Okay. So that's what changes in the free body diagram. In the equations, it's this black one, and so up is positive, so I'm going to have a minus F right there. Okay, so now, right, don't forget that. Okay, so what changes? Okay, so back up here, this equation is the one. You have a minus F. Okay, so let me just shrink this down. Okay, so I'm going to execute that, so I have slightly different formulas, and bang. Okay, so why is it that I'm only getting 2 of these? Okay, well, I have made a mistake, and I have figured out what my mistake is. Let me show you. Maybe you spotted it, but this formula right here, formula right here is baloney, right? So let's look back at the equation, or the picture. Y is at the top end of this rod, and Z is at the bottom end, and what I'm saying is that Y and Z are the same, and that's not true, because there's a spring in there. Oops, Big mistake. Oh my goodness, big mistake. How did I know I made a mistake? Well, I knew that I shouldn't be getting zeros because that force should have been influencing all of the objects. So, oh my goodness. So that's what it is. So I am looking for a constraint. How do I know that? Because there are 4 flow variables, no matter whether you're using the blue or the red. There are 4 flow variables, and there's 2 degrees of freedom. So there must be 2 constraints. This one is obviously not yet, so I'm looking back here and say, well, 2 of the 4 variables are in fact related. It's the beta and the y that are related, not the y and the z. Okay. So in this particular case, the distance that it moves, this point right here, that point right there, the distance that guy moves can be written in terms of beta, and it can also be written in terms of y. So that's what I'm going to do. So the distance that point moves using beta is going to be equal to r times beta, and that's equal to the distance y. And I have the plus minus sign properly because if beta is a positive number, then that point goes down, and y is also a positive number. So there we go. So that's going to be the constraint. So now let's go back to Mathematica and fix it. Okay, so there we go. And there we go. So it's this last equation here, which is wrong. And it should be r beta equals y. Bang. Those are my equations. And now I'm going to solve it. Okay, so let's enlarge this screen a little bit so it's easier to see. So here are the solutions. They're kind of ugly, but you might kind of expect that. The denominators are probably the same, if I'm not mistaken. They should be. So anyway, I've got, these are not quite the transfer functions because the F is the input. The T, the tension, TH, Y, and Z are my outputs, and beta, there's also a beta in there. Right here is the beta. So those are all outputs. Okay, so that is, I probably should have named it, so let's go back up here and call it, say answer 1 equal sign. So answer is this. You can try to simplify it if you want, but look at the denominators. The S is a 4th order polynomial. The order was 4, which is what you expected. You know it was 2 degrees of freedom. That's why I knew to find 2 constraint equations. So I'm pretty confident that I have everything that I need. So here's what I'm going to do. I'm going to define some values, and so we can proceed. So we're going to let K1 equal 1. We're going to let C1 equal 2. Let's see, I have a mass, I think, mass 3. We'll let that be 3. See, J1, we're going to let that be, I don't know, 2. Let's see, I think I've got other J's in there. Well, let's see. I'm going to execute this, and I'm going to ask for the answer, and we'll see what's left. Okay, I've got some K2s, so I'm going to go back up here. K2, we'll let that be 2. Let's see, I have an L, so L, we'll let that be 2. Let's see, what else do we have? Oh, R. We have an R, we'll let that be 1. Let's execute it and see, print out answer, see if we've got nothing but numbers now. J2. Okay, so we'll go back up here and we'll say J2 equals 4. Let's see, I think that'll do it, so we'll execute it, look at the answer, and I think we've got nothing but numbers now. Yep, nothing but numbers. And the transfer function denominator of theta is not the same as the others. I'm a little surprised by that. But anyway, let's take a look at it. I'm looking for this term. I'm going to copy and paste it. Let's see, copy and paste. Difficult without a mouse. So we'll copy, and let's solve this guy equal to 0. Solve for s's, and bang. I'd like to have it as a number, please. So I can put this, or just put a decimal point on any one of those guys, and it gives it to me as a number. The other thing I can do is take this one, copy, and I'm going to solve, and I know I'm missing that parenthesis, so I'll put it there. There we go, equals 0. Solve it for s, and let's put a number, a decimal point right there. Okay, so okay. It looks like the numbers are the same. I'll bet if I did a simplify on this guy, I bet it's the same thing. So let's take this. Whoops. Paste. And let's see. There's that missing parenthesis. Now just what I want to do is I want to simplify it. Simplify. And yeah, that's the same thing. You just factor it out to 2. So if you factor out the 2, you get the same denominator, which kind of makes sense. To me, anyway, it makes sense because they're all kind of tied together, and the motion of one is affecting all the other motions. So anyway, from here you can see that there are 2 frequencies. Right, there is this one in radians per second. The second frequency is this. It's 2 degrees of freedom, so you kind of expect that there might be 2 freedoms. You also have 2 potential time constants or settling times. So one comes from this number, and the other one comes from this number. You can't give 2 time constants, there's only the one, so what you do is you specify the longest time constant. So one time constant is either 1 over 0.02, 0.027. The other one is 1 divided by 0.033. And so what you would do is you would quote the longest time constant, 37 seconds. Okay, so that's that, and we'll turn off the recording.